Welcome everybody. Thanks Stefano for accepting our invitation to talk here today. Stefano is currently a postdoc at the INFN in Padova, and before that he was a postdoc at Case Western Reserve University in Cleveland, at the IAP Observatory of Paris and Technion in Israel, while he's got his PhD at the University of Padova. Stefano works in theoretical cosmology, large-scale structure of the universe, baryon acoustic oscillations inference, modified gravity and search for cosmic topology. Today he will present can we use baryon acoustic oscillation distances. Stefano, you can start please when you're ready.
Thank you for the very nice introduction and for this nice invitation. So I'm happy today to, with you, try to answer to this question. So let's move on. Oh, okay. So this is the list of my collaborators with whom I have been studying this topic for some years. So that's the outline. So in cosmology, what do we want in general from baryon-acoustic oscillations? So baryon-acoustic oscillations are meant to give us cosmology-independent accurate distance measurement, in particular the dark energy time. So today I will try to go deeper in the meaning of this sentence and at what level this is true. And then I will discuss new proposals and implications. So what is the goals of the BO distances? So the goals is to constrain cosmological models, in particular the dark energy time, as I said, and also to play with consistency test, for instance, what goes under the name of cosmological tensions. So how? So usually the BO distances are combined with other cosmological observations because in this way we can reduce the genesis among parameters, or the BO distances can be used alone, for instance, to detect to perform this dark energy detection test I will show you later. So let me show you a couple of examples from the Planck collaboration and the BOSS and SDSS survey. So in the left panel, we see probe combination. So the Planck satellite, when want to constrain the energy densities, use the BAO to break this famous degeneracy between omega m and omega k. And you see how BO are effective in playing this game. In the right plot, BO are used alone and is compared with different with other probes, and you see that they are really constraining. Here is an example when they constrain the equation state parameter for dark energy. But let's take a step back and revise quickly what is the idea and the picture that we have of the baryon acoustic oscillations. So in the standard model of cosmology, the initial fluctuation in gravitational potential, they are measured as temperature fluctuation in the cosmic microwave background. And here I show a plot from the Planck collaboration where you see how precise these measurements are these days. At late time, and the same oscillations are, they shows up in the Gauss correlation function, and they shows up as this peak and dip, this feature at around 100 megaparsec inverse H scale. So, so the standard model, the picture of the standard model give us for the BO is the following. So in the primordial universe, we consider the baryon photon plasma, and for each initial overdensity, under the opposite effect of baryon of pressure and gravity, acoustic waves was generated and it propagated until the baryon photon decoupling time at around redshift 1000. And there, so because of this decoupling, the acoustic waves got imprinted in the distribution of baryons, and following and given the following gravitational evolution, this got imprinted also in the distribution of dark matter. So in the matter distribution, we find this feature. So the idea of the ruler is that this length scale can be measured both from the CMB, from the cosmic microwave background measurement, and can be detected in the distribution of galaxies at date time. So two different time when we can measure the same distance. But what is the distance? The distance is called the sound horizon. and is defined as the co-moving length that has been traveled by an acoustic waves since the beginning of time up to the baryon photon decoupling time. So this length scale roughly corresponds to the peak position in the galaxy correlation function. And what is also relevant to build a standard ruler is that this length scale is geometrical, so it's independent of the premodel fluctuation parameters. So, but let's see in practice how we exploit this feature. So galaxy survey, with galaxy surveys, we usually measure redshift and angles, but we usually want to work in in co-moving coordinate. So to do this, we assume a fiducial cosmology, and because of this assumption, we have to work in fiducial co-moving coordinates. And so we are affected by the so-called Eichelon-Paczynski distortion effect. That means that a sphere in the right cosmology will look like an ellipsoid in the wrong cosmology. So the clustering correlation function monopole, redshift z, so this distortion can be precisely computed for the galaxy correlation function monopole, as we see here. So the distorted or measured correlation function is related to the true correlation function through these alpha parameters that is defined as the ratio of dV over dV fiducial, and dV is nothing but a combination of the angular diameter distance and the Hubble parameter. Okay, so what we want, so to obtain the cosmological distances we are interested in, we want to estimate alpha in a way that is independent of the background cosmological model assumption. And we should be careful if this is our goal, because in the Eichelon-Paczynski equation, on the right-hand side, we have model, we have the theory, and so we should be careful not to introduce unwanted dependency in this treatment. Okay, but let me stress again how BAO are relevant and they are used and they are considered to be reliable in cosmology. Here I just show two sentences from a couple of papers that are relevant for the combination of BAO with CMB or other or supernova, etc. So as you see, BAO are considered to be really reliable and constrained observable in cosmology. So I think it's important to go deeper in understanding of what this measurement give us and which assumptions are behind this inference. So let's start with this question: how cosmology independent are these measurements? So in practice, you will find that BO distances are employed in literature. They are employed to constrain any cosmological model. So the implicit assumption behind this practice is that BO give us accurate distance measurement that are cosmology independent. So this means that the inference is done without cosmological model assumption. So a question that I will ask is at what level is this true? We'll try to answer to this question. So let's go back to the slide I just showed you. That is the Eichelon-Paczynski equation, when on the right-hand side, the theoretical model should be treated with carefulness, because we don't want to induce dependencies that are not that we don't want. It can spoil our goal. So, but what complicate the games are the so-called late time nonlinearities. Some of them are low linear gravity, redshift distortion, scale-dependent bias, for instance. That is known since 15 years. Then they distort the correlation function in also the BO scales in a way that cannot be neglected. So this effect should be taken into account. So there are many different approaches, many different models. Probably one of the first one is this one, is what I call the minimal model for the Gauss correlation function, because it grasps the main phenomenology. So I use this model just to show you what is the game, because it's simpler to understand. So here you see the linear correlation function depends on the linear power spectrum, and depends on the energy densities and on the scalar spectral index, energy densities of baryons and cold dark matter. A is a scale independent but time dependent factor. That is the case for LCDM quintessence and flat geometry, quintessence models. It depends on their growth. So sigma naught, that is the damping factor that dump the BAO, as you see this damping here. This depends on the growth, on the Archangel's model, on the curvature, on the tracer. So what happens in practice? So in practice, this is the correlation function, and so we have to marginalize over the Archangel's dependent parameters as the smoothing and the amplitude. We want to fit for the dilaton parameter alpha, and we need to understand how we deal with the parameter that determines the shape of the correlation function as the energy densities and the scalar spectral index. Okay, so if we properly vary all the parameters that I just discussed, then dV will be estimated with a very large error. But after a while, we discover that there is a strong correlation between dV and the derived parameter that is indeed the sound horizon RD that depend only on the energy densities. So given this strong correlation, then the ratio between RD and dV is very well constrained at a level of, let's say, 1 or 2%, and this is really convenient. So this this analysis that we perform brought us the following understanding. So we can obtain cosmological distances that are geometrical, so independent of the premodal fluctuation parameters. Dark energy model independent, we don't need to assume on CDM or quintessence. Spatial curvature independent, and tracer independent. So we name these purely geometric Baryon Acoustic Oscillations. So it's not clear, I mean, and then if we move away from this framework, it's not really clear what happens. So for instance, for modified gravity cosmologies or dark energy, dark matter coupling, this probably depends on specific model, on the nonlinearities that this model has, and how far we are from the Planck best fit, from the Planck constraint, so we'll discuss later. So, okay, so then let's take a look to the standard BAO fitting approach that use what is called a template fitting. So this is the Yankel-Paczynski equation. Here is the data distorted, and here is theoretical treatment. So here there is basically the minimal model for the correlation function. And so the cosmological parameters are kept fixed, and some broadband term is added on the right-hand side. And this is chosen based on based on tests that show that is give us unbiased result in survey mocks and by the simulations. So in the end, so 5 parameters are varied, 1 is fitted, and B, A1, A2, and 3 are marginalized. And in principle, these extra parameters, they should properly propagate the errors that are not propagated because of this parameter fixing. But because of the cosmological parameter fixing, alpha will be biased, so then prescription is introduced to unbiased alpha, so this is multiplied by RD fiducial over RD true, where RD is the sound horizon. So then we can ask the questions, are errors on alpha properly estimated given these prescriptions? And so there are two problems in this game. The first is what I just discussed, is the parameter fitting, and the other is which correlation function model should we employ. Both 1 and 2, they can give us some, can have some consequence of the inference that we do. So the first problem, the parameter fixing problem, so we investigate, we did an investigation using Fisher matrix approach, and we compare the correlation function model fitting errors with the standard BO errors, and we found that the standard BO errors are underestimated by up to a factor of 2. Of course, we should, I mean, this is a Fisher forecast, and MCMC should be employed, even if this is not so simple, as I will tell you later. But there is the other question, that is, do we know the galaxy correlation function theoretical model? And so this is the state of the art of the approaches to predict the galaxy correlation function, or the clustering correlation function in general, if you want. So the state of the art is to use a numerical approach, to use simulations, for which we have ab initio and body simulations for dark matter. And then we use dark matter halo identifiers like friend, spherical overdensities, rock star, etc. Is in general too slow. They are in general too slow to run MCMC for data analysis, but in this direction, people are, there is a lot of work trying to employ powerful machine learning techniques to get around to this problem. But still, there is the problem of galaxies, because we don't have ab initio simulation for galaxies, because in general, we lack a complete predictive theory for galaxy formation. So also for this reason, we use prescription like a halo occupation distribution to decide how many galaxies fit in a halo to build our galaxy mocks. So how do galaxies precisely populate the matter field is still an open question. So then there are, because of these reasons, is widely employed to use a correlation function model as the minimal model, or many other models more advanced like that I will show you later. But in general, they are not as predictive as the embodied simulation. So we have several nonlinear effects like nonlinear gravity, rate space distortion, galaxy bias, how many parameters we put in which range of scales this correlation function, analytical correlation function model is working. So because of these uncertainties, the reference is to validate these models using body simulation plus galaxies in halos. Then the question is, what is the meaning of validating a model? We'll come back to this later, but before I want to show you a complementary approach that one can take that probably dates back to Peebles. And so, so the idea is that in the linear approximation, the observed correlation function is related to the matter correlation function through this scale-independent factor for LCDM quintessence, and we don't have to quintessence models, and we don't have to assume flatness. So if we have a preferred scales in the galaxy correlation function, this will be time and model independent. So this means that we can measure dV in a model independent way. So we wanted to exploit this approach, and let's say by chance we found an interesting point in the galaxy correlation function at BO scales. This is the midpoint between the peak and the dip. That's how we define it. And the interesting feature of the following is a geometrical point is independent of the primordial fluctuation parameters, is redshift independent at 0.5% level, so it's linear, so it's weakly dependent on nonlinear late time nonlinear effect. So because of 1 and 2, we can exploit it to perform background independent distance measurement. So how did we get to this idea? Well, that's because we did a wrong plot, meaning that we didn't really know how the BAO inference is working. So we divided by the growth factor of different redshift, and we saw that the correlation function was going through the same point. So then we started asking if this makes some sense, and in particular, if this can be used for cosmology somehow. So then we worked with the Ankel-Pazirski equation that can be rewritten in this way, with this definition of y, but that's the same equation. So then if you're at a linear scale, what we can do. So here we have the data, and we can use a model-independent parametric fit to estimate the linear point position and error. Then on the right-hand side, we don't need to use nonlinear theories. We just need a linear theory prediction that is given by the Boltzmann codes that we think we understand better, or if you want, we have a unique prediction. So then in this way, we can estimate dV in a proper way. We don't have to assume. So what we did here on the left-hand side still is the Ankel-Pazirski equation. We use an estimator to estimate the linear point position. We use a polynomial, but other approaches, of course, are allowed. We are not fixing parameters, and there is no fiducial cosmology dependence in this game. So we applied this to galaxy sample of the Boss collaboration, what is called the low Z and C mass galaxy samples. So we we validate the estimator, and then we estimate the linear point best fit and error. And what we got, we use pre-reconstruction data, and then we compare the linear point estimation with the standard BO estimation, and we found consistent result with smaller errors for these two galaxy samples. Yeah, so then also we we know that the BO are sensitive to the neutrino mass. Recently we analyzed, we use Boltzmann codes and the body simulation that take into account massive neutrinos, and then we should be careful in this game because now the scale dependence is already entering linear theory. But we found that the linear point properties are retained for massive neutrinos cosmologies. So then the linear point can be used also for this case, and so then it depends on the neutrino mass. The result will depend on the neutrino mass, so we can constrain the total mass of the neutrinos using this method. So let me go back to this question. So is the Gantt correlation function known? To answer to this, I will start showing you what is the validation that we employed for the linear point. So what we did, this is done with the Boss Galaxy MOX. So the theoretical assumption is that the correlation function is a smooth differentiable function that goes through the data, and then we assume a polynomial that is flexible enough to follow the data properly. So then we, as usually done, we require the estimation bias is small enough, so is like 5 times smaller than the statistical error. We got some mock acceptance rate, meaning that if you have a galaxy survey that is like small, so if the cosmic variance is large, the noise is large in general, so then the polynomial does not find a peak and a dip in some of the mocks. So then we will, so in this case, we do a conditional analysis, but is not usually the case. So this is not for the CMAS galaxy sample. This is not the case for Euclid, for DESI. So okay, so in any case, so we can use not any, but other linear point estimators. They are allowed if you want. Okay, that's this is a kind of a standard validation. So, okay, let me go back to the template fitting. So the template fitting, that is the standard BAO approach to estimate cosmological distances, is validated in the same way. Okay, but now it is not really an estimator. This is like here we have the prediction of the Boltzmann code of a galaxy correlation function. So it's a little bit more tricky, and we should remember, as I said, that there are late time linear effect that complicates the game. So then, in general, the correlation function model, I mean, you should have choices. So you should decide which fluid equations are used, what are the starting equations, which perturbation treatment you want to use. I mean, the most famous are standard perturbation theory, effective theory, large scale structure. Then you should decide which perturbative order you want to stop and how many parameters. So in the validation, usually the only rule is that we get unbiased result with respect to survey mocks, but what about the error estimation? So the error estimation is, of course, relevant. Here I show an example where we have k WCDM fake data. This is considered as a Euclid forecast, and they analyze as flat round CDM. So in this plot, in these parameters, we saw the parameter space. And you see there is this tension between AP and DV, and AP and DV are just a combination of the Hubble parameter and the angular diameter distance. And we see that there is a tension because, of course, we use the wrong model to analyze the data. Of course, there is tension if the model is wrong, but also the tension is determined by the size of the error bus. So then a strong tension can become a mild tension and vice versa. So we should be, of course, careful with error estimation. So then let me go back to the point relation function model validation. So we have to decide a range of scales, and the range of scales cannot be predicted as far as I know. So then we have this is usually determined with the galaxy MOX, or will be better defined with large embodied simulation. So how many range of scales? I mean, there is one for linear gravity, another for HP distortion, another for bias traces. This probably depend on the model. And parameters. So parameters are in general quantities that need to be measured from the data. What is the meaning of fixing them? Fixing some of them, we can get some misestimation of other parameters, but best fit and errors. Can we select parameters? So some parameters have a physical meaning, so probably we should be careful. So in general, this game is better played with large embodied simulation plus galaxies. Usually is done with survey mocks, not to underestimate the error. So in which sense linear point validation is different? So the theoretical input is that we want a smooth differentiable function. We don't need to have we don't have a unique estimator. We just use the polynomial because it's simple. So we can reduce parameters because they don't have physical meaning. The range of scales also can change because there is no physical meaning. The range of scales we choose to fit the peak and the correlation function in the peak deep range. You should fit the data well. I mean, it should be unbiased. We are limited by the embodied convergence by the 0.5% of this in the bias. So, and what about priors? For the correlation function model, what we did in the game when we use the Fisher matrix, we haven't put any formative priors. This can be unphysical, also because we saw that between prior and posterior there was a little gain. So the parameter range can be very wide, as we will see in a minute. So with MCMC we can enforce physical priors, but it's tricky not to use other observable priors because the priors will be really large and not to be too informative. So the linear point is we use a polynomial. The parameters, they don't have physical meaning, so we don't have this problem. We can do a conditional cosmological analysis. So for instance, if the linear point is detected, then for instance, we know that NS is larger than 0.5. So then in the introduction, I was discussing about the dark energy detection with the Baryon Acoustic Oscillations. That is an important proof in cosmology. And so how does that work? So we combine different BAO distance measurement, different redshift, and then we assume the Friedman equation, where omega k is a free parameter, and then we draw these posteriors. And as you see here, and the posterior is much wider than the Planck one. The Planck is basically here. So then the question is, but usually, okay, we have embodied simulations, we have survey mocks, all the our theoretical tools, they are very close to Planck. So can we trust? What is the meaning of this point here? So if you want to trust this plot, we should really push to have to explore this parameter range with embodied simulations, survey mocks, covariances, etc. Because the expectation of the BO distance is the following: the expectation is that the BO distances will be flexible enough to be used for many purposes. As I said, like for instance, Kenji detections, inverse distance ladder, cosmological tensions, and BO consistency test. So it's possible to use only, so in principle, it's possible to use only one BO distance. That, I mean, is one of the possible usage of the BO. So then the question is how wide the parameter range should be. And I will say, I mean, the widest possible, do what we can, but will be the goal. So what I said so far was without the so-called BO reconstruction. So let me introduce the BO reconstruction. This is important because the main product of the BO, the official BO release is done with BO reconstruction. And the idea is that basically because of late time nonlinearities, okay, the information is not the full information is not in the 2-point correlation function, but is also spread in the 3-point correlation function, 4-point correlation function, etc. So then it's interesting to try to get back the lost information in the 2-point correlation function. And this can be attempted using like sending back galaxies to their linear initial position. This is a little bit complicated, of course, and there are several treatments, and the first one uses only the top approximation, while there are more accurate treatment that were developed later. So, but in general, we can amplify the signal to noise and reduce nonlinear effect. So in general, in the algorithm usage, there is no error propagation. So the growth rate and the matter galaxy bias are fixed, given some lambda CDM, flat lambda CDM fit that was done before. So this, so in principle, this at least should be varied. I haven't seen this done, but I mean, there's a lot of work in attempts to improve the accuracy. Okay, so what are the caveats? The caveat of the standard BO is that the parameters are fixed to flat lambda CDM close to Planck best fit. And the BO reconstruction is done in basically the same way. So in general, we should be careful because for the analysis in general, like validation, covariance estimation, etc., a flat random CDM model is assumed for survey mocks and embodied simulations. And also the parameters are close to flat random CDM Planck best fit. The parameters of the cosmological simulation survey mocks. So we need to model linear physics for a wide parameter range. So what do we learn about cosmology when we play this game? So we want to test, the aim is to test cosmological models with galaxy clustering. So we compare data versus theory, we are testing cosmological models as assumption. So this will be simple if given a cosmological model, we have a unique galaxy correlation function prediction. So, to get around to this problem, a correlation function model usually is assumed, but I mean, this can be obtained adding extra assumptions. So when we compare data versus theory, we are testing cosmological models plus galaxy clustering model assumption at the same time. So it's legitimate to ask what do we learn about dark energy. So the linear point is nothing but an attempt to minimize non-cosmological assumptions, and is a more data-driven approach. So it's complementary in this sense. So why the linear point? So as I said, the correlation functional model has some, there is some unknown, in this late time nonlinearities are difficult to model. This is not a unique prediction. So with survey mocks, we can ensure that the results are unbiased. But what about the error estimation? So are we doing consistency checks or parameter estimation? Consistency checks, I mean, between data and survey mocks, for instance. So the linear point is a new theoretically defined observable, is the peak deep midpoint. It has interesting features. It allows to employ a model independent estimator. The errors are propagated. The errors are also small. The statistical errors are small. We are limited by the embodied systematic and by the 0.5% intrinsic bias. So the problem is that we have ab initio simulation for dark matter, but what about galaxies? We don't have an initial simulation for galaxies. We have to live with this, it seems. But in the meantime, we can ask if you're accurate enough with the embodied simulation. And here is an example. Well, this is something that we actually found during the years in our analysis. So here there are two simulations. One is called Abacus Cosmos, and the other is called Emulator, but they are both embodied simulations. They were combined to do some validation for BAO analysis. So then when we start playing with them, we found that the two simulations, if they have all the same setup, only a difference in the force softening definition, they gave linear point that was between them almost a 3 sigma tension. So then also the linear point is a secular shift that is that gives us 0.5% uncertainty. That is was found to be 1%, but more recently was found to be higher. But I mean but also is higher in some simulations, is not higher in other simulations. So what is can we really are the embodied simulation accurate at what level? And here is another example. So here is two embodied simulation, LCDM. The cosmological parameters are almost the same. So there is here you see a very small difference that for which we can correct. After correcting for this difference, we found this is the deep position in the dark matter field. And between the two simulations, there is almost sigma, around sigma 3 sigma tension. So can we claim the control systematics are better at 0.5%? I bet we're not even at 1%, but so then we should probably quote this systematics in the prediction of embodied simulation, at least. So finally, let me try to answer to the question I had in the first slide. Can we use Baryon acoustic oscillation distances? So the cosmological applicability of the standard BO distances is unclear. So for this reason, we have been analyzed and spent some time trying to understand the game. And so we came up with the following definition with the pure geometric baryon acoustic oscillation distances. So this means that we can measure distances in a way that is independent of some cosmological background models. So we don't have to fix parameters, we don't fix parameters to flatten on the CDM. In practice, we found two ways to deal with this. The first is the correlation function model fitting when we propagate all the errors. And with the Fisher approach, we found that the errors is underestimated by nearly a factor of 2 of the standard BAO. But still, we have the question of which model, how many parameters, and which vendor scales with which perturbative order, etc. So the linear point standard ruler is a complementary approach. It's more data-driven, so more model independent. So we don't need to assume a correlation function model to estimate the cosmological distance. There is a lot to do. So we should explore the wide parameter range. We should extend this to the quadrupole with the same treatment. Should combine with other observations, explore different galaxy populations, light cone effect, etc. Thank you.
Thank you so much. Thank you for the very nice talk. Do you have any questions?
I have a question, if nobody's asking.
Sure.
Do we know what is the effect on the two-point correlation function by other models? Like, is it very significant? Or because I saw that there are many uncertainties in the two-point correlation function. So, can we distinguish between, for example, having a curvature and having some kind of lensing and stuff inside?
You mean lensing, or you mean like modify gravity?
No, well, no. What I mean is that you listed a lot of uncertainties in the two-point correlation functions that were not related to the cosmological model. But what will happen if we also have not one the CDM but something else? Can we distinguish between all these uncertainties?
Well, that's a good question. Yes. Yeah, that is. I mean, your question is not really relevant for relevant for BO, but I think you are asking a more general question. So if you have a modified gravity cosmology, yeah, what happens? I mean, let me see if I have some background slide. Yeah, like this. So what happens if you're not standard cosmologies? So, I mean, yeah, usually we have another preferred scale, at least we have also other parameters. And so, like, it's not clear what happens to the linear point, for instance. And usually we have scale-dependent growth. So the growth is, I mean, in LCDM or quintessence models, the growth linear theory means that the correlation function is just rescaling. But if you have modified gravity, depending on how far you are from Planck, then you can have, I mean, there is no unique answer, also because we have to model nonlinearities. So depend on the model and also on the parameters that you assume if you run a body simulation, for instance. So it's difficult to give you a clear answer.
So basically, you need to make the n-body simulation in order to know.
To know the nonlinear effect, I will say yes. Yeah. Yes.
Okay, thank you.
Thank you, Erin.
Yeah, thanks for the nice talk. So what always bothers me about BAO is it seems like a black box, and the assumptions are, basically, like if any of your assumptions are wrong, it's difficult to diagnose signatures of, those assumptions being wrong. So let me give you just an example that bothers me is Lyman alpha BAO, right? If we fit the Planck cosmology goes through the middle of the BAO constraints. So if you wanted to improve the fit to, say, DM constraints and H of Z constraints, it's anisotropic BAO, you would end up with a kink in your Hubble parameter. Can we perceive this as some sort of, signature of something going wrong, or like what is the signature of, your assumptions breaking down, right? Do you understand the question that I'm trying to ask?
I'm not sure, but I mean, so yeah, for instance,
could we ever reach an inconsistency? And then we would see that this is an inconsistency, and then we realize that one of our assumptions is wrong.
Yeah, so probably, okay, so it's difficult to find inconsistency when you talk about error estimation. Okay, usually people discuss about bias. Okay, and this is a more delicate game because depends on the priors, etc., etc. But for instance, here, if you explore a wide parameter range, that is something that is not done because. So if you really want to be serious, let's say with tensions, we should stop like moving 5 sigma from Planck because 5 sigma from Planck these days is very small. So then if you relax this assumption and then we start moving in all the parameter range, then we will see what happens. That is my understanding at least. But then also, I mean, so, and then we should be careful in thinking that our BO measurement is independent of any cosmological model. That is something that is. But if you use this BO measurement that you perform assuming like lambda CDM or close to lambda CDM, and then you use this for whatever other model with very open priors, with very wide priors, you can get completely wrong result. So I mean, the question is depend on how careful you are in taking into account all the information that you have or you don't have. This is one of the clearest example, I think, when it's clearly shown that the BO, they can go very far away from Planck. So then we should treat this properly. I don't know if I answered your question.
Okay, thanks. I think that partially answers my question. But you would still be assuming the lambda CDM model somewhere, right?
Here, yes. In this game, yes.
Okay, thanks.
But I think, but I mean, so one of the problems that we have in general, I'm not saying just about the BO, but in general, is that all the data analysis, for clustering in particular, for Planck probably, or for CMB probably is easier. There is a strong assumption of lambda CDM in the data analysis. Like all the survey mocks are lambda CDM, flat lambda CDM in particular. So then is kind of dangerous. All the observational systematics, they are tested and removed with lambda CDM mocks or embodied simulation. So then you don't really know what happens if you move away from it.
Thanks.
Thank you. We have a question in the chat, Simone. What about the angular BAO distance? You focus mainly on dV, but I know it's possible to obtain dA, for example, using angular correlation function, though this problem applied the same.
If you had the same problem, well, you have still nonlinearities, for instance, right? So then you have to understand how to deal with nonlinearities if you just use the angular BAO. And then, well, there are different approaches, but usually the approach is similar, if I'm not wrong, is similar to this one. So still you are not now in moving coordinate, you use the angular coordinate, but still you have some template and you fix some parameters. There are approaches that are not that used when they assume a template for the correlation function where there are no fixed parameters, but still you have a phenomenological model that is very that is not as you are assuming something with this model because you are assuming that there is a dump done in some way. You are assuming some connection with the underlying RD. So then is calibrated. So this methodology is calibrated on embodied simulation. What is good about this is that there is no fixing of cosmological parameters, but still there is let's say calibration of the fitting. I mean, here you have like something Xi that is not Xi fixed, but is still a template. I don't know if this makes sense. I don't have a slide about this, but
Thank you. Hector?
Yeah. So the whole thing about the factor of 2 in error bars between what you say that you get on the methodology, which uses essentially alpha parallel alpha perpendicular parameterization. So what you're saying, I'm sure it needs like a bit of more demonstration, right? Let's put it this way, because I mean, you can claim that the error bars are underestimated, right? But then this should have some impacts on other stuff. So for instance, if you redo this kind of analysis in like many mocks, and then you compare the average of error bars of each of these mocks, and then you compare that with the dispersion of best fits, then definitely you would see something weird because
no.
the best fits would have some inner prior. So you would tend to have like larger dispersion of best fits, but still like different from the average of the error bars on each of these best fits. So this is one thing, but this was checked by the EVOS collaboration many times, and there was
Yeah, but this we already discussed about this, but this is something that you can do. I mean, you can decide how many if you treat this as an estimator, that this is a model, so it's not an estimator, but if you treat this as an estimator, then you can do whatever you want. You put parameters you want.
What you're claiming is that the error bars of this estimator are underestimated. So
But
I'm saying
I claim something different. I claim that we shouldn't use this as an estimator. We should consider this as a model.
No, but what you said is that the error bars of this estimator are underestimated.
Yeah, because
by a factor of 2. This is what you said.
Because if you treat this as a theory, so as a model, then you have some parameters.
Yeah, I understood the reasons why you were claiming that. But then one thing are the reasons, which I would address after. But then first of all, I mean, if this were independently of the reason, what you would see is that when you figure the dispersion of this estimator on different independent realizations.
No, you don't.
Yeah, definitely. Because yes, I tell you that you do, because putting information. So if you put information on your model, which is what you are claiming, you're saying I fixed the template, so I put information, and therefore, because I put information, I would get smaller error bars than I should if I were agnostic about this information. So if you do this, and then you check the dispersion among different realizations, then you would see that the error bars of each of these realizations, they are significantly smaller than the actual dispersion of best fits. This is one thing. So this has not been shown in any papers or anything that you've published or anyone has published?
Can I answer you, or you, if you want to go ahead? So, like, let me make you an example. Like, if you are like in a famous example, okay? If you like the Planck, if you have the Planck CMB data and you fit with flat lambda CDM or with lambda CDM without assuming flatness, you will find very different error bars, and they are. I mean, if flat lambda CDM is a right model, they are both of them. They are consistent, but in one case you have an extra parameter, so your error bars are larger. I mean, when you have a model,
What you're saying here is not about the. I mean, obviously you choose
about the
the
model.
model, you
No,
open the
it's about
parameter
the model.
space, your error bars changes. But what you're saying here is about the ratio of dV over RD. This ratio is model independent. Essentially, each ratio it doesn't depend on the model. This is essentially the position of the peak. It's something which is model independent. So it doesn't matter the model you choose. This ratio is
model independent.
the position of the peak.
Here you have a theory. You don't have an estimator here. Here you have a theory.
You have to think on the data. dV and over RD is something that is not on your model, it's on your data, it's the position of the peak.
No, it's not on your data. On your data, you have a two-point correlation function. The only way to estimate some cosmological parameters is if you have interposed a model. Otherwise, I mean, it's not coming from.
I think that was key. But then let me go to the second step, which is even more important, because what you are saying here essentially is that the reason for this factor of 2 is that you are fixing the parameters of your template. You were saying that in slide 34, I think, we're saying, well, you were saying that was fixed. Okay. So what you can do is an alternative approach to this, right? So you can essentially take your correlation function and choose a range of scales where essentially isolate the BEO and then do a full fit to that, right? In terms of the parameters of the model. So now then you drop anything about alphas, about DVs, and then you just fit omega mater, age, and whatever parameters you want, right? And then if that was, I mean, and here there is no fixing of parameters of the template. There is no template anymore. The template varies. So it's like an EFT thing. So you just essentially vary your 2-point correlation function model in each MCMC step. And then you get an error bar on the parameters of the model, omega mater, age, and AS, for instance, if you put a BBM prior or whatever. And then you compare these error bars and these measurements with the ones derived from the alphas, which are coming from the fixed template model. And then you would see that these two agree very, very well. So this factor of 2, I mean, this should appear here clearly, because, I mean, if you vary the model, then you should get more information, as you were claiming, but you don't. So yeah, I mean, this is, I think this doesn't make any sense to me. I mean, this should be like more supported, and there are like many things and many papers you are like not mentioning here, and that they are going against this statement.
Can I answer? So there are 2 points here. The first is that in this, so when you compare the correlation function model fitting varying all the parameters, you should have that alpha is a free parameter if you want to play the game of the BAO first. Yeah, so then if you do this, then you will have difficulties with priors, because here, okay, if you want to do an MCMC, then you should put priors that are much wider than Planck 5 sigma priors. This is not done anywhere. So this test done with the MCMC instead of the Fisher matrix is not done in any paper.
Yeah,
with the problem.
It's not in paper. People have done.
It's not done.
Fits to the BAO.
No, it's not done. I mean, what people do is they fit the correlation function, but without leaving this as a free parameter. In that case, alpha is not.
No. That's not true. There are people who have done that.
No, there is nothing. There is no proper fit when the priors are much larger. They are wider enough. When the correlation function is fitted in this way, when you vary all the proper parameters, as I said here. This is extremely difficult because the priors will be very, very wide. This is not done.
I mean, it's done for like at least for lambda CDM model.
What people
Done.
do, they do the fit when alpha is no more a free parameter. That is the idea of the BO. Where alpha is a derived parameter. But that's not again. If alpha is a derived parameter, then dV, because dV depends on the energy densities, okay? Then you are fixing lambda CDM. Well, you are fixing flat lambda CDM basically, and then your error bars shrink a lot. But that's another game.
No, I mean, when you do full fits, then you have to choose a model.
If you
There's no way, you can escape from that. So
yes, no. This is not
yeah.
no, but that's not true. That's what I explained here. That if you do a full fit, you can still, I mean, because you analyze how the correlation function depends on the parameters, okay, and then you marginalize over the energy dependent parameters, then you can still estimate alpha in a way that is a free parameter, and this will encompass some cosmological models like quintessence. You don't have to assume curvature or whatever.
That's the compression thing. So when you work in terms of alpha as a parameter of the model, not as a derived parameter, then yes, you can constrain at the same time many models, because this is an effective compression of the BO.
It's not only a compression.
This is not
It's not only a compression. It's the fact that you encompass several different models if you do this properly. So then your error bars
get compression of the BO information, and this compression.
So basically, let me tell you. So basically,
something it's known from many times. But
basically, if in this fit you fix dV, so dV is not a parameter here, or dV is a parameter, then your results are really different.
Here, dV cannot be a parameter of the model, because you vary omega baryon, omega C, NS.
But it's completely consistent.
dV is a derived parameter in this.
It's completely consistent. It is the right parameter if you assume a model. If you don't assume a model, if you say that also, I mean, you take into account the models that behave as lambda CDM, like quintessence models. It don't change the shape of your linear correlation function. In that case, that is fit, this is the idea of the BAO, is take into account other models as quintessence models. Okay, so in that case, dV is a free parameter, and then, but the good point is that, you get larger error bars, but then dV can be applied afterward to other models. If you fix flat lambda CDM, then it's only for lambda CDM.
There are other questions in the chat. One, thank you for the great talk. Correlation function of rich clusters in the local universe has a maximum at scale 120, 140 h to the minus 1 megaparsec. How this affects the analysis of the CFs you described in your talk, error bars, etc.
So I think it's talking about the correlation function of clusters. Is that, did I understand?
I think you can read the chat.
Sorry.
So it's my question. It's correlation function of rich clusters in superclusters in the local universe. There was a series of papers about that, but it was a long time ago, maybe you don't even know, in 1997, 98. And they have very strong maxima at the scale, which is like a higher than POA scale. And why it's so and how it affects your analysis. Is it some additional factor to take into account, or whatever? Because you mentioned correlation function, you have to take into account how galaxies populate the dark matter.
Yeah. Yes. Yeah, so I'm not sure. I have problems in hearing, sorry. But I think you are talking about the correlation function of cluster in the local universe?
Yes, because those were like the farthest superclusters in those studies. They were traced by able clusters, but they were like at distances like up to Sloan Gate Wall and farther away.
But you are talking about the correlation function of clusters at the BO scale or some other scale? Because
some larger scale. The scale is 120, 140.
Okay. Yeah. So
larger scale.
yeah. So basically, people are playing the BAO game also with correlation function of clusters. In that case, you will have the same problems. The only difference is that the tracer, I mean, the tracer is not a galaxy, but is a cluster. So you have less objects, they are more biased. But then, I mean, still the game is similar. You test them with very large and accurate embodied simulations, and you can play the same game. Indeed,
Sorry, I agree with you, but you need huge simulations for that.
yeah. You need huge simulations, and also they should have very high resolution, like similar to the Euclid fluxus simulation, for instance, if you want to have.
May this scale in the distribution of clusters be related to Baryonic acoustic oscillations or some other process, in your opinion?
People measure the point correlation function of clusters, and they actually detected the Baryon acoustic oscillation feature. This was done in the last 10 years or something. If I understood well your question, I think that's the answer.
Well, if this scale is related to Baryonic acoustic oscillations, this is a bit large. Like Brent Alli
But which
estimate.
scale? So you are saying, sorry, let me try
Maybe
to.
you can write in the chat because we can't hear you very.
Yes, I understand, but I say that this scale is too large to be.
So, okay, you're
Baryonic
saying that
acoustic oscillations.
people detected a scale that is like a feature at a scale that is larger. You mean H inverse megaparsec around 120, 140?
Yes, which is certainly larger than POA, which should be
Yeah, for sure it's larger
109.
than this. And it's not compatible because the error bus is small enough. I don't know. I mean, I haven't seen this measurement in the last years, at least.
Okay, I put this reference into chat.
Okay, thank you.
Thank you.
Thank you. We have another question. I think it's the last one. Thanks for the talk. Is the effective field theory or large-scale structure more model independent of the standard BAO approach? If yes, was it the drawback?
Well, I mean, it's let's say, so the effective field theory large-scale structure is a theory, okay, to predict the. So let me go. Yeah, is a correlation function model, basically. So then is a way that you can using embodied simulation, you can predict. Okay, you can fit the correlation function at some scales, at large scales, because that does not work at small scales. And then you can decide to use it to play the game of the BAO. So then you can study for which parameter, I mean, for which cosmological models that is for sure quintessence and LCDM, without assuming weighted for the curvature. And then you can study all the parameters dependence on dark energy and do the same game that I showed here for this very simplistic model, that is this one. So you can play the same game if you want to estimate alpha in a way that encompasses some cosmological model. Or you can, but so far this is not done because it will be difficult because of the very wide prior. What is done so far is that the effective field theory prediction or prescription is used to fit the correlation function, assuming a specific cosmological model. And then you get constraint, you don't, dV is not a free parameter anymore. It's something different, let's say.
Okay, thank you.
Thank you.